All right, so today we're looking at the natural log and solving logarithmic equations. So quick review over things that we've already done. Let's expand a few of these, right? So show blue so we can really see what we're doing here. So expanding, remember looking at the top first, we have multiplication. So we're going to make this addition. So the log base 3 of y plus log base 3, and this is radical x, but we want to write this as an exponent, so x to the 1/2 division, so we're going to be minus the log base 3 of 5. Then we want to deal with this exponent. Remember, exponents come out front, so we're going to have log base 3 of y plus 1/2 log base 3 of x minus the log base 3 of 5. All right, next. Once again, we'll rewrite this as an exponent, remembering, of course, that we have this. And in this case, because the 1/2 is of the entire thing, we're going to bring this out first, and then we're going to split it apart. So 1/2 times the log base 5 of 25x. Did anyone see the mistake that I made? Yeah. What's the square root of 25? Exactly. So let's go back and let's do that first. So let's simplify this. So this actually becomes the log base 5 of 5x to the 1/2. Now let's split it apart. Multiplication, so it's addition. So the log base 5 of 5 plus, I think we're smart enough, we can handle moving the exponent first, 1/2 the log base 5 of x. Oh, condense the next one. All right, so you see this big, giant, lovely mess here. Let's put it together and see if we can make it a little neater. All right, so exponents first, bring them from out front and put them behind. So this is going to be log base 2 of j to the 8th minus the log base 2 of k to the 9th plus the log base 2 m to the 2/3, but let's actually write this as a radical. So this is going to be m squared and then the cube root of it. All right, and then we're condensing. So once again, subtraction means division. So this is going to have a division bar, and addition means multiplication. So this is going to be the log base 2 of j to the 8th over k to the 9th cubed root of m squared. Once again, at this point, I am really not worried about rationalizing this. Go ahead and leave that radical in the denominator. At this point, I do not care. We're going to leave it there. All right. Next, we're introducing a new base. So let's talk about the number e. This is Euler's number. You're saying, Ms. McMullen, how do I get Euler? This is E. So E-U-L-E-R is a man. It is actually pronounced Euler. Don't ask me why. I have not a clue. Generally, when I say this and I read it and I think of it in my head, I say Euler. So if you want to say that in class and say Euler instead of Euler, I am not going to jump you. That is absolutely fine. Just know that if you hear someone else talking about it and they're proper math people, they're going to say Euler's number. So know that Euler's number is this funky little script E. All right, so Euler's number is an irrational number, which means it never repeats. It's like pi. You know that pi is equal to 3.1415926, and it goes on and on and on and on and on and on and on forever. Okay, Euler's number is the same. So E, can I just approximately equal to here, is approximately equal to 2.7182818828, and it goes on. There are a lot of 8s, but it never repeats. That's what irrational means, is it never repeats or terminates. It just goes on and on and on and on forever. All right, so the natural log is a log that is base E. So the log base E of a number. All right, and we write this as ln, the natural log of x. All right, so just like you remember from way back at the beginning of this unit, we talked about the log base 10 of x. We just write it as the log of x. So when you don't see a base, you know that it's 10. This is the same way. Log base e is written as ln of x, the natural log of x. All right, we don't need to write a base because when we said ln, the natural log, we understood that it is base e. All right, so let's take a look. Let's solve some equations below that involve the natural log and e. All right, so remember, anytime we see ln, we know that the base is e, and we want to convert this. So remember, when we're converting, and it works the same with natural logs as it does with regular logs, so we're going to change these places. This becomes my exponent. So e to the fourth equals x. And we can actually put this in our calculator. The calculator should have a little e button. And in fact, on mine, I've got one that looks like this. It's e to the box. So I'm going to push that. So e to the box, and I'm going to put 4 in the box, and I'm going to hit equals. And this means x equals, and again, 3 decimal places, please, 54.598. All right, so now let's look. Natural log of e to the e equals x. All right, switch them places, and this becomes the exponent. So e to the x equals e. So x we know equals 1. Or we could have looked at this right up here at the top. Remember our shortcut that says anytime our base and our y are the same, that the answer is 1. So we could have known that right up there without even converting. Next, e to the x power equals 9. So how in the world do I do that? All right, well, let's convert this back to a log and see if it makes any sense, makes a difference. All right, so remember, when we're converting it to a log, these two switch places. This reduces to a subscript, so the log base e of 9 is x. So then I'm going to say the natural log of 9 equals x, and you should have on your calculator a natural log button. In fact, I do, it just says ln. So the natural log of 9 equals 2.197. Remember, 3 decimal places, and we want to round. All right, the natural log of x equals -4. Remember, natural log is base e. So let's rewrite this as an exponent. Switch these places. This becomes an exponent. Log disappears. So e to the -4th power equals x. All right. So what is e to the -4th power? Let's plug it into our calculator. E to the -4th equals, and my trusty Casio tells me it is x equals 0.018. Is everybody getting the hang of this? Convert from one form to the other, plug it into the calculator. All right, solving with logarithms on both sides. So if log base b of m equals the log base b of n, then m equals n. Okay, and I know you're saying, what now? All right, just follow me. All right, if I had said x, y equals x, z. All right, we know x equals x. So if I divided both sides by x, the x's would cancel out. And that would just leave me with y equals z. So if these are equal, then y has to be equal to z. Same way here. If the two logs of the same base, notice the same base, are equal to each other, then the y values must be equal to each other. All right, so let's look at an example. So step 1, if necessary, condense on both sides. Remember, only one log or natural log. Per side. Okay, so what I'm talking about is look right here. You see how I've got the natural log of 7 plus the natural log of x minus 2? We don't want that. 1 log or natural log per side. So this is addition, which means if we're going to condense it, it's multiplication. So we would say the natural log of, same base, so we can do this, of 7 times x minus 2 equals the natural log of 6x. All right, and since we've got this, let's go ahead and distribute this. So the natural log of 7x minus 14 equals the natural log of 6x. Now let's keep this in parentheses just for clarity. All right, step 2, as long as the logarithms are the same base, set the y values equal to each other. All right, so the y values, that's the stuff in the parentheses. Okay, so set the stuff equal to each other. So 7x minus 14 equals 6x. Okay, next, solve for the variable. And remember that you must check. All right. Remembering that the log of a negative number is not allowed. All right, so let's check. Let's solve and check this. So I want my x's by myself and the numbers by itself. So if I move this 6x over here, move the 14 over there. So I get x equals 14. All right. So then let's plug this back into our original equation. And we can go original or we can just go right up here. All right, and let's right up here. And let's check it, shall we? So 7 times 14 minus 14 equals 6 times 14. Plugging this into my handy dandy calculator, I get 84 equals 84, and that checks. We are great. All right, flipping the page over. Now that we know our steps, let's actually practice a couple. So solve each logarithmic equation for x. Be sure to check for extraneous solutions. That's the checking. Make sure that your solutions work. All right, these are the same base. They're already simplified. I only have 1 log on each side, so I need to set the y values, set the stuff equal to each other. X plus 7 equals x. Now wait a minute here. If I subtract x from this side, I get 7 equals 0. Well, that doesn't work. All right, so this one is a no solution. All right, don't be afraid of getting a value, an answer that doesn't work. Sometimes there isn't a solution. Now, that doesn't mean that just because you don't feel like doing the work, you can write no solution on the test and it's going to be all right. Don't get lazy on me. All right. Okay, next one. Let's condense these guys. All right, first move your exponents. So the log of 4 squared plus the log of x equals the log of 2 to the 5th. All right, let's do something about these numbers to their exponents. So 4 squared, we know that's 16. 2 to the 5th, we know is 32. Just go ahead and simplify these guys while we got them. All right, condense this side. Both have the same base. So we're going to multiply them. So this becomes the log of 16x equals the log of 32. Set the stuff equal to each other, set the y values equal to each other. So 16x equals 32. So x equals 2. Once again, we want to check that. Plug that right back in. And so, well, 2 times 16. It does give me a positive number, so we're good. All right, next. Log of base 5 of 3x minus 4 equals the log base 5 of x plus 2. All right, before you start going to town and expanding this guy, Remember, we don't want to expand. We want them condensed as much as possible so that we only have one log on each side. And that's exactly what we got. So now we can set the stuff equal to each other if our bases are the same. Notice I've got a base of 5 on this side, a base of 5 on this side. So let's set the stuff, set the y values equal to each other. So 3x minus 4 equals x plus 2. And then let's solve for x. I can subtract x from both sides. And then let's add 4 to both sides. In algebra 2, you can handle doing 2 steps at once, right? So leaves me with 2x equals 6. Divide both sides by 2. So x equals 3. Plug my 3 in up here. Make sure that neither of these are negative. Remember, we can't have a negative number. So 3 times 3 is 9, minus 4 is 5. We're good there. 3 plus 2 is 5, and we work. That's good. That's our answer. Look at the next one. The natural log of 3x minus 1 equals the natural log of 7x minus 8. We both have the same base. I only have one log or natural log on the same side, so we're good. So set the stuff, the y values equal to each other. So 3x minus 1 equals 7x minus 8. Let's get our x's on the same side. My bigger x is over here, so I'm going to move this one over to the right. So minus 3x minus 3x. Add 8 to both sides. Once again, we're doing 2 steps at once, but we can handle it. So negative 1 plus 8 gives me 7 equals 4x. Divide both sides by 4. So I get x equals 7 fourths. And if we plug that in and check it, we can tell that we're correct. Everyone's starting to get this. All right, so let's scroll down here. Let's do the very last one. All right, the last one is generally the most complicated. Let's just see what happens. So I'm looking, and I've got 2 logs on the same side of the equal sign. I need to condense those together, making sure they are the same base, and they are. So let's condense them together. Noticing this is subtraction, so this is going to be division. So this is going to be the log base 5 of x plus 3 divided by x plus 2. Parentheses just for emphasis, for clarity, equals the log base 5 of 5. All right, we have the same bases, so we can set each piece equal to each other. So x plus 3 over x plus 2 equals 5. Then we're going to get these things by itself. So let's first multiply both sides by x plus 2. With that. So I get x plus 3 is equal to 5x plus 10. I got the bigger x's over here, so I'm going to subtract this x from both sides. And then I'm going to subtract this 10 from both sides. So positive 3 minus 10 gives me negative 7 is equal to 4x. Then we're going to divide both sides by 4. So I get x is equal to negative 7 fourths. Let me try that again to make that illegible. Negative 7 fourths. And if we plug that in and check it, we'll see that it does indeed check. Real quick, since we still have some time, I want to go back and let's look at this last example here. All right. Once again, we have 2 values on the left and only 1 on the right, so we need to condense these. They have the same base. They're both natural logs. So it's addition, so we're going to multiply them. This becomes the natural log of x times x minus 2 equals the natural log of 8. Let's go ahead and do our multiplication here. This becomes the natural log of x squared minus 2, parentheses for clarity, equals the natural log of 8. We have the same bases, so I can set stuff, the y values equal to each other. So x squared minus 2 equals 8. Oh, and hey, look, it's quadratic. You all remember that quadratic unit we just finished? All right, which means we need to set this equal to 0 so we can solve it. So I'm going to subtract 8 from both sides. Forgot to write my x and I multiplied. So then I get x squared squared. It is not wanting to write that. Let's try this again. X squared, there we go, minus 2x minus 8 equals 0. My go-to method for solving these is factoring. So let's see if we can factor this sucker. Negative 8. Two numbers that multiply to get negative 8 and add to get negative 2, negative 4, and 2. Perfect. So this factors to x minus 4, x plus 2. We set each piece equal to 0. So x minus 4 equals 0. X plus 2 equals 0. Solve for x. So x equals 4. X equals negative 2. All right, and then we plug it back up into our equation. So let's see, right here, we need to see if we plug it in, we need to make sure we don't have a negative number. So negative 2 squared is 4 minus, so negative 2 times negative 2 is 4. 4 plus 4 is 16. Well, that works, but let's look back up here at our original. If I plug in a negative 2 here, can I do that? The natural log of negative 2, am I allowed to have a negative number there? No. All right, so this negative 2 doesn't work. Make sure when you're plugging it back in, you're going all the way back to the originals to check for negatives. So this does not work. And if we plug in 4, we'll see that it actually does. All right, we are done, guys. Make sure you email me if you have any questions or send me a message through Canvas. Have a great day. See you later.